This is AP Calculus AB, and in this video I'm going to talk about section 4.4, derivatives of exponential and log functions. Now I will tell you in this video I'm not going to go through a ton of examples for you because really what this is a set of derivative rules that you need to practice with. So primarily what I'm going to do is go through a few examples and show you how they work, and then you're going to practice some problems, and I'll just kind of go through the solutions and give you some things to look out for when you're solving these types of questions. This is our last section of derivative rules. So we've piled a lot of derivative rules in the last couple of weeks. We've gone through all of our basic derivative rules: power rule, quotient rule, product rule. We went through all the trig derivative rules. We went through the inverse trig derivative rules. We went through the chain rule. And now we're going to add on these exponential and log rules. Now, this looks like a bunch of new rules, and there's really only a couple rules here that you're going to have to remember. And a couple of them are special cases of the rules that you're seeing. So you can see with these exponential derivative rules, the most common one that we're going to see of these is the derivative of e to the x is e to the x. Now, that can be proven using the definition of derivative, but in terms of how are we going to see this? Well, usually we're going to see it in this form. The derivative of e to some power is equal to e to the u du dx, just using the chain rule. Now, that e to the x rule is actually a special case of the a to the x rule. So this is just an exponential expression where we have some base a, and it's raised to the x power. The derivative of that is a to the x natural log of a. So like I said, the e to the x is just a special case, because if I make this natural log, or e to the x natural log of e, the natural log of e is just 1. So really, this is one rule, and we've got 3 other versions of that rule. But I would remember this probably just because we use e to the x so often. I would probably remember those 2 rules, remembering that we do have to use the chain rule when the exponent on our base is not just an x. All right, so then we also have these log derivative rules. And again, it looks like 4. It's really 1, and then we've got some special cases in here. So the most common one we're going to use is here. The derivative of natural log of x is 1 over x. And we can prove that rule using the definition of derivative, or we can modify the e to the x rule, and we can manipulate that, and we can create a rule for natural log of x from that as well. But in the end, this is the rule that you end up with. So that's the most common form we'll see it in. But remember, you've got to use the chain rule if it's natural log of anything other than just x. Now, that rule is actually just a special case of our general log derivative rule. So this is a log of any base a. When I take the derivative of a log with a base a, it's 1 over x natural log of a. So again, if it was a natural log, well, that means it's a base e, and we'd have a natural log of e there. It would become a 1. So that's why the natural log rule is just a special case of that one. So in the end, just like on the last one, I would probably make sure to remember these 2, remembering that I have to account for the chain rule when the argument for the log is not just an x. All right, so let's take a look at a couple examples, and then I'll have you try some of these. So these are really, really simple derivative rules, and more than anything, it's just a matter of practicing with them enough that you've got the rules memorized. So this is an example of e to the u, this first problem. So for my derivative, I would have e to the u, e to the x squared plus 5x times du dx. Well, the derivative of u here would be 2x plus 5. And that's my solution. That's it. Just basically one step. Really, really simple. All right, so for 2 to the x, that's an a to the x type of expression. So the derivative is just going to be 2 to the x times the natural log of the base, which in this case is natural log of 2. Okay, so again, very, very simple. Most of these aren't really very algebra intensive when we're dealing with these exponentials and when we're dealing with the logarithms. So you'll find these, for the most part, to be pretty quick, easy questions. For this next one, we have x natural log of x minus x. Now remember, the first 2 I gave you there were sort of isolated. We didn't have a lot of extra derivative rules coming into play. But we can combine all these derivative rules together. So you can see things like product rule and chain rule and quotient rule and all the things that we've seen before. So for this one, I've got a product rule situation showing up. So x natural log of x, well, the derivative of x is 1. So it's 1 times natural log of x plus x times the derivative of natural log, which is 1 over x, minus the derivative of x, so minus 1. In the end here, I've got natural log of x. X times 1 over x is 1, so I have 1 minus 1, so this just turns out to be natural log of x. So still not that difficult to do. The last one here, it says the derivative with respect to x of log base 5 of x. Well, remember, we've got a rule for that. So it's 1 over u. Our u here is square root of x times the natural log of a, which in this case our base is 5, times the derivative of square root of x, which at this point you probably just know that's 1 over 2 root x. And when I simplify that down, I'm going to end up with 1 over 2x times the natural log of 5. Okay, so again, not anything too tricky from a simplification standpoint. All right, so the last thing I want to show you here is what we call logarithmic differentiation. Sometimes you're going to run into functions that you don't have a derivative rule for. But if you modify the form that the equation is written in, you can apply a rule that you already know. It's sort of like what we did when we came up with the derivative rules for the inverse, the one that I showed you for inverse sine in the last video. So what we're trying to do here is we're trying to take the derivative of y is equal to x to the x power. We can't use the power rule because our exponent is not a constant value. We can't use the exponential rule because that base is not a constant value. So we're sort of stuck. So what I'm going to do, as you can tell from the name of logarithmic differentiation, we're going to use logs to manipulate this equation to allow us to take the derivative. And what I'm going to do is I'm going to take the natural log on each side of the equation. So I'm not really changing the equation because I'm performing the same operation on both sides. I'm just changing the form of the equation. And what that allows me to do is rewrite this as natural log of y is equal to x natural log of x. Well, that is something I can differentiate. So I'm going to do that over here. The derivative of natural log of y would be 1 over y dy dx. And then we just did the derivative of x natural log of x on this previous problem. If you remember, these two terms were the derivative of x natural log of x. So I know that's going to end up being natural log of x on the right side. Or you could go through and do the product rule and simplify down to natural log of x. And then, so we'd have that plus 1. So remember, it would be 1 times natural log of x plus natural log of x times 1. Or excuse me, 1 times natural log of x plus x times 1 over x. And then I'm going to multiply the y over because I'm trying to isolate dy dx. So dy dx here would be equal to y times all of this, natural log of x plus 1. And the last step here, remember at the beginning, we know what y is. Y is x to the x power. So our derivative is going to be equal to x to the x times the natural log of x plus 1. So what I really did there was I just created a new derivative rule. Now I know what the derivative of x to the x power is by using logarithmic differentiation. So when you run into functions where none of the rules that you know apply, this is one of the things that you can try. And sometimes we can even use this on problems that it might not be obvious that you would use logarithmic differentiation, and I'm going to show you some of those in class next time. So what remains here are a bunch of practice problems. So on this page, you've got 7 practice problems dealing with all those different derivative rules. And then on the last page, more practice problems. So what I want you to do is take a little bit of time and work through these problems. They don't really take that long. So work through these problems. And then when you unpause the video, I will show you the solutions and I'll just point out any unique things that might show up when you work these out. Okay, so here is the first one, the derivative of e to the tangent x. So the main thing, just remember to use your chain rule, e to the tangent x times secant squared x. The next one is a natural log. So 1 over u, 1 over 5x cubed minus 7x times du dx. The derivative of u is 15x squared minus 7. So again, really nothing to do there in terms of simplifying. Here we've got x over 2 times log base 2 of 2x. So we're going to have product rule involved. We have the derivative of the log involved. We have the chain rule involved. So there's a few derivative rules we need to know. So the first part here, I did the product rule. I did x over 2 times the derivative of the log. So 1 over 2x, natural log of 2 times the derivative of 2x is 2, plus the derivative of x over 2 is 1/2 times log base 2 of 2x. And then it was just a little bit of canceling here and simplifying down. Now, I put this in here just as a reminder what this derivative notation means. Capital D with the subscript x means the derivative with respect to x. So we have natural log of x to the x power. Now, since we're dealing with logs, try to keep in mind that you can use your log properties. So in this case, I can bring that x down and make it a coefficient. And now what I'm really taking the derivative of is x natural log of x. And we've seen that a couple of times now. That's just going to be natural log of x plus 1. So remember to think about log properties when you work through those problems involving logarithms. Also in this section, it's not really necessary, but they put in this section because there's a proof for it in here about taking the derivative using the power rule when you have irrational exponents. So here we've got y is equal to x to the square root of 3 power, but it's just the power rule. Bring the square root of 3 down times x to the square root of 3 minus 1. It's nothing different than what we did before with the power rule. But I put that in there because you might see a couple of homework questions on it. Just follow the same power rule that we've always been using. On this question, you might have been a little bit confused because it says arctangent. Whenever you see arctangent, remember, we're dealing with functions. So we're always going to use the function version of those arc trig functions. So if you see arc cosine, arc sine, arctangent, just treat it as an inverse sine, an inverse cosine, an inverse tangent, in this case, inverse tangent. So I'm essentially taking the derivative of inverse tangent of e to the x. So I have 1 over 1 plus u squared, which is what you see right here, times du dx. The derivative of e to the x is just e to the x, and then I just multiplied it through. So again, pretty straightforward. Now on this next page of problems, or actually let me show you this one first. This one's kind of messy, but it's simple. The main thing that I wanted to show you here was the idea of using an exact solution. So we have 2 to the x minus 1 as our function, and they said at what point is the slope equal to 8? Well, if I want the slope to be equal to 8, I need to set the derivative equal to 8. And that's what I did here. So I've got this equation that I'm trying to solve. At that point, I have a lot of different ways to do it. I isolated 2 to the x. I chose to use a natural log because that's typically what we're going to use, but you could use a log of any base. Like I could have done a log base 2 there, and then my answer would be in terms of log base 2. And I would still have an equivalent numerical value, but my answer would look a little bit different. But in the end, as an exact solution, I have this messy looking x. Probably not that practical to have my solution in that form. And when you start to get into numbers that look like this, a lot of times it's better to convert it to a decimal because, I mean, who can really quantify what natural log of 8 over natural log of 2 divided by natural log of 2 is? Who can really estimate that in their head? Not very many people. But if you wanted the exact solution, that's what it would look like. And then to get the corresponding y, I go back to the original equation. Okay, so keep that in mind. With these exact solutions, they can look a little bit messy, even though the algebra is fairly simple to solve them out. And in terms of what base do I use for my log to solve, if it's a free response question, it doesn't matter. If it's a multiple choice, when I get to this step, I usually look at the answers and say, okay, what log base do they have in the answers? And if they have a log base 2, I would use a log base 2. If they have a natural log, I would use a natural log. So just take that into account when you're working through those type of questions. All right, and then on this last page, these were a little bit harder. We have natural log of secant x plus tangent x. So it's 1 over u times du dx. The only thing that's harder here is you have to remember your trig derivative rules. But this one actually simplifies down. So my 1 over u was 1 over secant x plus tangent x. My du dx was secant x tangent x plus secant squared x. And then if you notice here, you can factor out a secant from the numerator and you'll get a secant x plus tangent x, and it'll simplify down. This next one, 3 to the 2x times 2 to the 3x squared. It's not anything tricky. It's just a little bit messy because we've got product rule. We have the derivative of an exponential function. We have chain rule involved. So it's just a little messy from that perspective. And then my simplifying, I had to do a little bit of algebra. But you can see that I decided, rather than writing it as 3 to the 2x and 2 to the 3x squared, to simplify it a little bit, I wrote it in this form. If you took the derivative and your answer is in terms of a base 3 and a base 2, and you have natural log of 3 and natural log of 2 in there, that's fine. You're going to have an equivalent answer to mine. It's just going to look slightly different. So keep that in mind when you work through those. Sometimes you can do little algebraic things like that to make the problems easier on yourself. This next one, x to the 2x plus 3 power. So again, we have a base that's an exponent, or excuse me, that's a variable, and we have an exponent that's a variable. So this is a situation where I would want to use logarithmic differentiation. This is very similar to that x to the x problem. So I took the natural log on each side. You can see on this first step. And then from there, I just took the derivative of the equation in the form that it's in. And then I just solved for dy dx and substituted in for y, x to the 2x plus 3 power. And you can see, typically when we do this logarithmic differentiation, we're going to have messy looking derivatives. But that is the derivative of the function. It doesn't look really nice, but if I need to know dy dx for any x value, I just plug that x into that equation and that will give me the derivative. Okay, and then this one we had natural log of e to the x minus natural log of y equals e to the y. The big thing that I wanted to point out here, again, use what you know about simplifying these logarithms down. Rather than messing with natural log of e to the x, I just rewrote that as x. Because if I take a log base e and I have an exponential base e, those are essentially canceling each other out. And I just get x. And then from there, I just took the derivative implicitly to get y over y e to the y plus 1. Okay, and down here at the bottom, this was a little bit more conceptual. It says, if the limit as x approaches b of g of x is equal to k, then which of the following must be true? Okay, so it says the limit of the function exists. That doesn't tell me anything about the derivative. It doesn't tell me whether or not the function is continuous, because I'd have to know, is the function value equal to the limit value? Again, it says g of x is defined. I don't know that. If I knew what the function value was, I could say that. And then it also says g of b is equal to k. And again, I don't know that. If it was continuous, d would be true, but I don't necessarily know that. So that's just a little bit of review, thinking about the idea of continuity. And then we've got this problem here. We have y is e to the negative x natural log of x. What's the derivative at 1? So just apply the product rule, take your derivative, and then plug 1 in, and you'll end up with 1 over e. And the last problem here, which of the following functions has a derivative at x is equal to 0? So if you were to go through and actually take the derivatives on all of these, you would see that for 2 and 3, they exist. Now, if you actually take the derivatives and work them out, that's kind of what you need to do. The one thing that I would point out here is, remember that that's the same as y is equal to, when we're greater than 0, it just looks like x squared. And when we're less than 0, it looks like negative x squared. And it doesn't really matter where I put the equal to sign, but that's what that function is, written as a piecewise function. And now if I take both the derivatives, I get 2x and negative 2x. At 0, those are the same, so that function does have a derivative at 0. So you can do similar things with the other ones. You can take the derivatives, and then you can just see if the derivative exists at 0. All right, so that's everything in this section. The big thing is there are essentially 4 new derivative rules that you need to know. So make sure you practice a lot with those. And like I said, practice a little bit with this logarithmic differentiation. We'll talk about that a little bit more next time in class, because there are some other special cases where logarithmic differentiation will become a useful tool for us.